All right, so we are up to method 3 for solving quadratics. Method 1 was solving by graphing, which is just looking at where your x-intercepts are. Method 2, solving by factoring. And now we're at method 3, solving using square roots. Solving using square roots is really quick and easy. It just only works in certain situations, and it requires you to be able to work with radicals a little bit. So the first thing that we're going to do is we're just going to review simplifying radicals a little bit, and then we'll talk about the actual solving down the bottom. Okay, so first off, basic rule for simplifying radicals. For all a and b such that a and b are real numbers, so they're not imaginary, and the product of a and b is also real, then the square root of the product is equal to the product of the two individual square roots. And similarly, the quotient of the two is also congruent to the square root of the quotient is is the same thing as the quotient of the I'm sorry, you know what I'm trying to say. I'm trying to say this, right? I got it really good on this first one, and the second one I just totally lost the right order that those words needed to go in. All right, so basically it's just saying you can either multiply first and then take a square root, or go the other way. Or you can divide first and then take a square root, or square root and then divide. Okay, so that's the trick that we're going to use. So simplifying radicals, there are two different ways to do this. I am going to show you both ways. I do not care which way that you use. It is a total personal preference. Okay, so method 1 doing this is you look for two numbers that multiply up to 40 in this case, where one is a perfect square. Okay, so for this method, right, for your perfect squares, I think I'm going to color code here. So our perfect squares are numbers that are just squares, right? So one's a perfect square, but not particularly useful when you're doing this. 4 is a perfect square, 9, 16, 25, 36, right? That's 2 squared, 3 squared, 4 squared, 5 squared, and so on, right? Okay, so they keep going from there. So you're looking for one of these perfect squares that evenly goes into 40. You want to ideally get the biggest perfect square that evenly goes in. In this case, that would be 4. So I'm going to rewrite this as the product of two square roots, 4 and 10. And then since 4 is a perfect square, I know the square root of that is 2. And then I end up with 2 root 10 as my answer. Okay, I know I'm done because 10 doesn't break down any farther, right? I can break this only into 2 times 5, and neither one of those is a perfect square. So there's no more perfect squares that go evenly into 10. All right, so that is method 1 for how you're going to do this. All right, so let's actually do another one of these. So before we do method 2, let's take a look at 54. So for 54, I'm looking at these perfect squares, and I'm looking for the biggest perfect square that evenly goes into 54, which would be 9. So I'm going to break this into the square root of 9 times the square root of 6. Square root of 9 is 3. And then the square root of 6, there's no other perfect squares that evenly go into that, so I know I'm done. Okay, this guy over here, the only thing that would be different is that we're going to have this 2 chilling out at the front. So I'm going to focus on the 75. I need a perfect square that evenly goes into it, 25. So I'm going to rewrite this as 2 times the square root of 25 times the square root of 3. Okay, the square root of 25 is 5. The square root of 3 is just the square root of 3. That doesn't break down anymore. And then meanwhile, we've been the whole time, right? This is 2 times, 2 times, 2 times. So it's still 2 times. And then I can multiply the 2 and the 5 and get 10. Okay, so that's method 1. That's the perfect square method. Okay, so that method works really well if you are familiar with your perfect squares and you're good at finding factors. So if you can look at something like 54 and be like, oh, what goes into 54? So that's where that method works. There's a second method, which I call the birthday cake method, that involves looking at prime numbers. Okay, so prime numbers are numbers that don't break down anymore, so you can't divide them by anything else. So 2, 3, 5, 7, not 9, because that's 3 times 3. So the next one would be 11, then 13, and so on. So there's numbers that don't divide any smaller. Okay, so how you do the prime number method, the birthday cake method, is I'm going to start with this 40, and I'm going to put like a division symbol, like a long division symbol, and I'm going to divide it by any one of these prime numbers. Doesn't matter which one, totally a preference. Okay, I'm going to start with 2 because 40 is even, so I know it divides by 2. So 2 goes in there 20 times. I'm going to put another division symbol, so another prime number that goes in there. Well, 2 will go in again. 2 goes in there 10 times. Okay, another division symbol, and I need another prime number that goes in there. 2 still works. Oops, goes in there 5 times, not twice. Right, another division symbol. I need a prime number that goes into 5. Well, 5 is itself prime, and 5 divided by 5 is 1. Okay, so you can kind of see it looks like a little birthday cake, like one of those tiered birthday cakes, and like up at the top, that 1 is your candle. That's why we call it the birthday cake method. Okay, so what you're doing now is now that you've got it in prime factorization, we're looking for those perfect squares. So I'm looking for pairs of numbers because any pair of numbers is going to be a perfect square, right? So pairs are going to go on the outside, and anything that's left over without a pair stays on the inside and gets multiplied back together. And that's where that 2 root 10 comes from. So the 2 comes from your pair, and then the 5 times 2 multiply back together to give you the 10. Okay, so with 54, same deal. So I'm going to take 54, prime number that goes into it, well, divides evenly by 2. So I can do 2 into that 27 times. Okay, prime that goes into 27, 3, goes in there 9 times. Right, and then 3 goes into 9 3 times. And then 3 goes into itself once, and there's my candle, right? Then I'm looking for pairs. They don't necessarily have to be next to each other. I tend to go through and just do the same prime number until I run out of them, but they don't have to be next to each other. It's just pairs. Okay, and then I've got a pair, so that's going to go on the outside. Anything left over, this 3 and the 2 that don't have pairs, you multiply back together. Okay, this guy, I'm going to ignore the 2 on the outside for right now, so I'll start with a 75. 5 goes into 75 15 times, I believe. Right, and then 5 goes into that 3 times, and then 3 goes into that once. There's my candle. Here's my pair of 5s. So I have the 5 on the outside, a 3 on the inside. Meanwhile, that 2 has been floating around in the front, so that's still there. And I get 10 root 3. Okay, so 2 different methods for doing this. Again, I don't care which one you do. It's just a matter of which one's faster. And sometimes it's a nice thing to have in your back pocket to be able to do either. Because sometimes I can look at a number and be like, oh, like if I'm looking for the square root of 800, I can look at that and be like, oh, well, 100 is a perfect square that goes into that right away. And that'll break it down for me a lot easier. So I'd use method 1. Okay, but sometimes I'll just end up with weird numbers that I don't know what perfect square goes into it. And that's where this method helps out a lot. Okay, so you can do either. It does not matter which one you want to do. All right, so let's take a look at these guys, and I'm going to kind of switch up. I'll do one method, one the other. So when I'm looking at square root of 6 times square root of 8, I'm going to multiply that together. 6 times 8 is 48. And then from there, I'm going to figure out what this is simplified. Okay, so I could look at this, all right, and say we were going to look at this, and I'm going to use method 1, and I look and I say, oh, well, 4 is a perfect square that goes into that, right? So I could break this into square root of 4 times the square root of 12. And then you get 2 root 12. Okay, here's the danger of the first method. That is not fully simplified because I can break this 12 down. There's a perfect square that goes into 12, right? So from here, I could then say, okay, well, I broke the 48. Now I can break the 12 into 4 and 3. I've still got this 2 on the outside. Okay, so then the square root of 4 is 2. I've got this 2 still hanging out, and then the 3. So I'm going to get 4 root 3, okay? And that's my final answer. Okay, so if you'd noticed from the get-go, 16 actually goes into here. 16 goes into 48 3 times. But if you don't notice that, that's all you're going to do is you just have to make sure that you take an extra layer and break it down a little bit more. Okay, so just watch out for that. All right, now this guy I'm going to take a look at and do using kind of my birthday cake method. So when I multiply these together, I'm going to multiply the numbers in front together. So 3 times 2 is 6, and then 5 times 10 is 50, right? And then from there, I can birthday cake this. So 50, I know 5 goes into that 10 times. I know 5 goes into that twice. And then I know 2 goes into that once. There's my pair. So I've still got this 6 on the outside. Now I've got a 5 from my pair, and then the leftover 2. So that's 30 root 2. Okay. Now, birthday cake can be really nice when you're looking at a method like this. Just as an example for you of where this is kind of convenient to know how to do. So just on a little piece of scrap paper here. Okay. Another thing that you could have done looking at these And these ones are pretty simple. Let's look at the 6 and the 8, right? Is you could have said, well, I know 6 is 2 times 3, and I know 8 is 2 times 2 times 2. And then you can go right from there and look for your pairs rather than actually multiplying the numbers together. For 6 and 8, really not that big of a deal. But if you were multiplying, say, the square root of 12 times the square root of 15, right? I don't know what 12 times 15 is off the top of my head, but I do know that I can break 12 down into 2 2s and a 3, and I can break 15 down into a 3 and a 5, and there's my pairs. Oh, that's going to simplify to 6 root 5. Okay, so it saves me the step of actually multiplying those. So both methods are really useful depending on what you're doing. All right, awesome. Last one, division. Okay, so the rule with division is that you can either square root first and then divide, or divide and then square root. So when we're looking at, say, this guy right here, where these are both perfect squares, I'm just going to say, well, let me split this up, and I'm going to do the square root of 25 is 5, and the square root of 4 is 2, and I'm done. Okay, so that was really convenient. All right, now sometimes though that doesn't happen, and there's a rule with radicals that you are not allowed to have square roots in the bottom of your fractions. Okay, just like how you're not allowed to have decimals inside of fractions, you can't have square roots in the denominator. And the reason for that actually goes back to the days before calculators. If you kind of think about if you didn't have a calculator and you were doing some division. Okay, so say you wanted to do the square root of 3 divided by 2. Okay, well, if you don't have a calculator, you probably somewhere, because at this point they know about square roots, right? So somewhere you've got a list of all the decimal equivalent of what the square root of 3 is. And if you wanted to divide this out using like long division, you could, right? You could say, okay, well, I know the square root of 3 is 1 point, blah, blah, blah. I'm just making numbers up because I don't actually know what it is, right? And then when I want to divide that by 2, you can approximate an answer because you can say, well, 2 goes into 13 6 times, right? And do long division, bring down the 2, blah, blah, right? And figure out, oh, it's about this decimal. Okay, so this guy, you can handle that if you don't have a calculator. But if it's the other way around, think about how you'd handle that. So you'd set up your long division, the 2 would go in here, and then out here, you'd have to like somehow, and again, I'm just making up numbers, you'd have to somehow like write this number that goes on forever, right? Which you can't even fit the whole thing there. And then when you're trying to like do the go into it, right? The way that this works is you say, well, 2 doesn't go into 1, but it does go into 13 6 times, right? How do you do that with this guy? I mean, I could add on 0.000, but this literally goes on forever. How do you even begin to approximate that? So if you don't have a calculator, this problem you can't do, but this problem you can. Okay, so that's why there's this rule. Square roots in the top are okay, square roots in the bottom aren't. Okay, there's some debate now in mathematics about whether or not we should even bother to continue doing that, but we are falling on the side of yes, we should. So, because obviously we have calculators now, so if the rule is because it's inconvenient for calculators, right, why do we need to? But anyway, what we're going to do, so your goal here is to get this number at the bottom to be a perfect square. Okay, so there's a couple ways you could do that. You could start by simplifying the square root of 8, and then from there figure out what you have to multiply by. But personally, if it's at all possible, what I'll do is I'll just say, well, I have an 8. If I multiply 8 times 2, I'm going to have 16, and that's a perfect square, right? So I'm going to multiply top and bottom by root 2. That's going to give me the square root of 10 on the top and then the square root of 16 on the bottom. And I know the square root of 16 is 4. And the square root of 10 doesn't simplify. So that's it. I'm done. Okay, no square root in the bottom and totally simplified. Okay, so then same thing over here on this guy. I want to make this into something that's a perfect square. Well, what can I easily multiply 12 by to get to a perfect square? 3. That'll get me to 36, right? So I'm going to multiply top and bottom by root 3. So that'll give me 8 root 3 over root 36. And then I know the square root of 36 is 6. So it's 8 root 3 over 6. But then see how the 8 and the 6, those are both outside of your radicals and they have a common factor. So simplify that like a fraction. 2 goes into both of those. So it's going to be 4 root 3 over 3. They simplified 8/6. You didn't do that here because this number is inside of a radical and that one's outside of a radical. So it doesn't work. They've got to match. They have to either be both in radicals or both outside of radicals. Okay, so that's the hard part. Okay, so that's the tricky part, is making sure that you remember all of your radical rules. What we're actually looking at today that should be new, because this should all be review, the new stuff is just solving with square roots. Okay, and this is pretty easy if you can do all of the tricks with radicals. So let's take a look at a couple of these. So first of all, take note that this only works solving with square roots in kind of two situations. It's got to be a situation where there's no b value. So notice how there's an x squared, but there's no bx term here. Okay, so you got to make sure that there's no just x by itself. You got to just have an x squared somewhere in there. Okay, now when you look down here at these guys, these are also candidates because it's a quantity with the x in it squared, and there's no other x's chilling out anywhere else. So it sort of fits into this form. It's a little bit different. Okay, so that's the thing that you got to watch out for here. You got to make sure that you just got that x squared somewhere and no other x's. Right, and then all we're going to do is I'm just going to square root both sides. Okay, so this one I'm going to get x equals, and then we need the square root of 49. And you're thinking to yourself, oh, that's 7. Move on to the next one. But is it? 7's not the only number that when you square it, you get 49. Right? If you square -7, you're also going to get 49, right? So you're actually going to have two answers here, +7 and -7. And the way we usually write that is we just use this symbol. It looks like a plus sign over a minus sign, represents positive or negative. Okay? So watch out for that. This is the most common mistake. So this guy here, square root both sides, right? And I'm going to get x equals positive or negative. And then the square root of 40, well, we already simplified that up here. That's 2 root 10. So that would be my answer. All right, now this guy, I got to get the x squared alone before I can do my square rooting. So I'm going to add the 5 to both sides. I'll have 3x squared equals 24. Divide both sides by 3, and that's going to give me x squared equals 8. And then I'll square root both sides. And I'm going to get x equals positive or negative. And then the square root of 8, let's see, I can break that into root 4 times root 2. So that's going to be 2 root 2. All right, this guy over here, this one you're thinking to yourself, wow, that looks complicated. The first thing I'm going to do, though, is I'm going to get rid of this fraction. Okay, this still fits in this form because even though I've got x squareds in two different places, these are like terms, I can combine them. So like you could do some fraction work and make this like 6/3 and then add them together and go from there. But what I'm going to do for my first step is I'm just going to multiply this entire equation by 3, right? Giant distributive property. So in this first one, the 3's will cancel. I'm going to get 2x squared. Goodbye fraction. 3 times 2x will be 6x squared. And then 3 times 4 is 12. And then that's 8x squared equals 12. X squared equals, when you divide by 8, I'm not going to use decimals. I'm just sticking with fractions here. So I would end up with 12 over 8, right? And 4 goes into both of those. So I can simplify that to 3/2. Okay, when I square root that, I'm going to get x equals positive or negative square root of 3/2. And then you got to rationalize it. So I'm going to multiply top and bottom by root 2. So my final answer here is going to be positive or negative root 6 over regular 2. Be careful about whether your square root covers the whole thing or not. Okay, yes, that's how you have to write your answers. No, you can't write them as decimals. All right, this next guy here. So the first thing I'm going to do here, don't be tempted, right? Don't multiply this out or try to distribute. First of all, exponents come before multiplication. So you have to square this first, right? But if we do that, we're going to end up with a bx term, and then we can't solve by square roots. So what I'm going to do is I'm going to divide both sides by 3. Make that x minus 2 squared equals 9. Then I'll square root both sides. So x minus 2 is positive or negative 3. And then when I add the 2 to both sides, I'm going to get either positive 3 plus 2 or negative 3 plus 2, right? So my two answers are going to be 5 and -1. Okay, this is a really common mistake area because what a lot of people will tend to do is they won't put the plus or minus in here. They wait till they get to the bottom and they say, oh, well, 3 plus 2 is 5, so my answers are positive and -5. Okay, so that's a really common mistake. Make sure you add the plus or minus in as soon as appropriate. Okay, same deal over here. So I'm going to start by dividing by -2. This is just reverse order of operations. So that's going to give me 20. Then I'll square root both sides. So that's going to give me positive or negative. And then 20 is 4 times 5. So that's going to be 2 root 5. Do out some scrap work if you need to. Okay, and then when I subtract the 6 from both sides, okay, what we're going to do, right, is we're going to subtract the 6 from over here so these cancel. And I'm going to subtract it over here, okay, but it's not like terms with that one because that one has a radical. So I'm just going to write this as -6 plus or minus 2 root 5. Technically, you could write it as positive or negative 2 root 5 minus 6, okay, but generally speaking, we always put them in this order. It's just sort of like the approved order, I guess, is to put the square root at the end. Okay, so that's how you'd leave your answer. Again, no decimals, always simplified radicals. Okay, so that was kind of a long day for something that's really not too terribly hard, but solving by square roots. So that is method 3. So you should be able to solve by graphing, you should be able to solve by factoring, and now solve using square roots.